Lesson 5.8, Coordinate Proofs. So today you get a new type of proof called a coordinate proof. What you do is you place a geometric figure in a coordinate plane or graph. So you draw a graph of something, some shape. And then when your variables are used for the coordinates, so in other words, instead of a point being 1, 2, maybe the point is AB. The result will then be true for all figures of that type. So use triangles, use variables for the corners, and then we use formulas to prove things like the midpoint formula, the distance formula, and the slope formula. And you can see they're all there in your notes for quick reference. All right, so to place figures in a coordinate proof, here's some things. Use the origin as a vertex or a center. Well, that makes life easy because that gives you 0. The origin is 0, 0. And it's easy to do math with zeros. And then if we place at least one side of the polygon on an axis, that'll give us more zeros, because if it's on the x-axis, the y value is 0. If you're on the y-axis, the x value is 0. Usually you keep the figure within the first quadrant. That makes all the numbers positive, and most students prefer positive numbers. And we're going to use coordinates that make computations as simple as possible. So that means we're going to try to set it up so we don't get things like fractions if possible. So if you want a midpoint, instead of saying we're going from 0 to a, if we go from 0 to 2a, then the midpoint would just be at 1a. And again, we're going to prove things by calculating slope, distance, and midpoints. Here's a sample placement. This is a rectangle. And you can see we used an origin for one of the corners. And because of it's a rectangle, we know we have the right angle. So we can put one side on each axis. And notice in the coordinates, that gives us another 0. Makes it easy for math. But then I don't know the length and the width, so I just made up letters for that. It's h and k, which means this other point is over h and up k. That's why this one is hk. For a generic triangle, you might have this. Notice, again, vertex is at 0, 0. One of the sides is on an axis. That gives us another 0 there to do our math. But we don't know any relationship between the rest of the points, so I just have a D and F and a G just to give us other points. So what could we do? Well, with a rectangle, we could do things like prove the diagonals are congruent. Or with this triangle, I don't know what you could prove. You could prove that the medians intersect at the same point or something. So let's place a square in a coordinate plane so that it's convenient for finding side lengths. Then we're going to assign coordinates. So you'll need to draw the axes, and then we need a square. Remember, we want to put one vertex probably on the origin, and then finish drawing our square. Well, if it's a square, what do you know about the sides? And we're going to assign coordinates. That one's 0, 0. That one's easy. How long shall we make a side? I don't know. How about the length A? And it's up 0. So it's over A and up 0. Well, over here, this point is over 0 and up. Well, it's the same distance because it's a square, so it's also up a. And our last point would be over a and up a, so a. And there we go, we have a square. Let's try another one. Let's place a right triangle in a coordinate plane so it's convenient for finding side lengths. All right, so if it's a right triangle, where do you suppose you'd want to put the right angle? That's right, probably here at the origin. So you'd probably want to make your right triangle like that. If we assign coordinates, that'd be 0, 0. How long shall we make this leg there at the bottom? All right, A. And so then we could make the other leg some other length like B. And there we go, we have a right triangle. We could do things like Pythagorean theorem. Maybe. Prove that. All right, let's place an isosceles triangle in a coordinate plane with those vertices, and then find the side lengths and coordinates of the midpoint of each side. All right, so here we are. I've already drawn the picture for you. I just plotted those 3 points. Now I don't know how far A is, so I just guessed. And then I want to find the side lengths and the midpoints of each side. So maybe we could start with, how about PQ? Remember the distance formula is x2 minus x1 squared, y2 minus y1 squared. So for PQ, that would be x2. Then x1 is negative 2a. y2 be a. y1 would be 0. Well, we could simplify that. 0 minus anything is the anything. And it's minus a negative, so that makes it plus. So I have 2a squared and a squared. So 2a squared, 2 squared is 4. And 4a squared plus a squared, it'd be 5a squared. And well, we can square root each of those. The square root of 5 is the square root of 5, but the square root of a squared is just a. So it's a times the square root of 5. Let's leave a space for the midpoint, and let's do QR's distance. Okay, so x2 is 2a, x1 is 0. y2 is 0, y1 is a. All right, so this would be 2a squared. 2 squared is 4a squared. And 0 minus a is negative a squared, comes positive a squared. Negative a times negative a makes positive a squared. So then I have 4a squareds plus another a squared would be 5a squareds. So I have the square root of 5, but the square root of a squared is a. So notice PQ and QR are the same length. All right, our last side is PR. And you could probably look at that and figure it out, but let's use our formula anyway. All right, x2 is 2a, x1 is negative 2a. y2 is 0, y1 is 0. All right, so I have 2 minus a negative is a plus 2, so that's 4a, and it's squared, and then 0 minus 0 is 0. The square root of 4 squared is 16, a squared. But the square root of 16 is 4, and the square root of a squared is a. So PR's length is 4a. So that's different from PQ and QR, which is why it's an isosceles triangle. Two sides are congruent. Now let's look at the midpoint. The midpoint's formula is x1 plus x2 over 2, y1 plus y2 over 2. So the midpoint of PQ is, well, x1 is negative 2a, x2 is 0. And y1 is 0, y2 is a. All right, so here on the top, negative 2a plus 0 is negative 2a, and 2 divided by 2 is 1, so it'll just be negative 1a. On the second one, 0 plus a is a over 2. So the midpoint of QR. x1 is 0, x2 is 2a, y1 is a, y2 is 0. So I'll have 0 plus 2a, which is 2a. And 2a divided by 2 is just 1a. And the second part, I have a plus 0 is a divided by 2. Notice the symmetry. Negative a, comma a over 2, and positive a, comma a over 2. And then the midpoint of PR. x1 is negative 2a, x2 is 2a, y1 is 0, y2 is 0. So the first one I have negative 2a plus 2a. When you add and subtract the same thing, you get 0. And then the second one, you have 0 plus 0 is 0. So its midpoint's right there at 0, 0. There we have it. We have all the distances and all the midpoints. So let's do an actual proof using a coordinate proof. So we're given this picture and the coordinates, and we're supposed to prove TOU, so that angle, congruent to VUO, that angle. Well, how could we prove those angles congruent? Well, if these segments were parallel, then they'd be alternate interior angles. So could we prove those segments parallel? Well, if they're parallel, they'd have the same slope. So let's find the slopes. Remember the slope formula. It's y2 minus y1 over x2 minus x1. So let's start with the slope of OT. y2 is k, y1 is 0. x2 is m, x1 is 0. K minus 0 is k, and m minus 0 is m. So there's our slope. Let's do the other segment, VU. So let's find the slope of VU. y2 is k, y1 is 0. x2 is m plus h. x1 is h. So on top of k minus 0 is k. On the bottom, h minus h cancels out, and I'm left with m. So notice they have the same slope. So what's that tell us? It tells us OT is parallel to VU. Well, what's that tell us? Well, that tells us the angle TOU is congruent to angle VUO by the, what kind of angles were these? That's right, alternate interior angles theorem. And so notice the coordinate proofs are not two column proofs, it's some calculations and writing things out. Fun.